Hi there, this is the last video in this series where I will summarize the entire takeaways from the class, but there is one bit that's remaining, and that is categorical variables. So far we have looked at variables that are continuous variables, like for example, salary, right? Age. They are continuous variables. There are lots of data points, but let's say if a variable is like male or female, then there's only one or two outcomes, or like education level, right? You could have a high school, or you could have a postgrad, or you have less than high school. When you have those variables, then and real life will have lots of such variables that are categorical. So how to deal with categorical data when we do our regression is important. So let's take an example. A male categorical variable, and we call this a dummy variable. Why we call this a dummy variable? Because male doesn't just mean male. It means when you say male as the variable, it can take in two values, 1 or 0. And 1 could stand for 1 means male, 0 means female, or vice versa. Whatever the convention is that you use, you can put any association. That's why it's called dummy. But you need to remember what association you've made. And that variable can take two forms. It can either be 1 or 0. So it's not male as the text male. It's a variable that can, when it is 1, means it's a male. When it's a 0, it means a female. So when you have such a variable, you can then look at like the data for the CPS data, where you can look at from the United States sample data, are the men paid more than women? That's one question. Let's say you want to answer. And the second question you are trying to answer is, are the men paid more than the women controlling for their experience? Meaning, what if I wanted to even remove the experience out of the way? Then what is the impact of experience on male versus female? So if you have more experienced male, let's say you have a 3 years experienced male and a 3 years experienced woman, do they get treated the same or not? First, I want to just know male and female, and then I want to know what is the variation for experience. So the way we do that is we now have a dummy variable called male, which will take in 1 and 0. So we will go through our data set and we will make every row that's a male 1 with that variable, and 0 for every row that is a female entry. Once we have that data set of who's getting paid how much, we can run a regression, and we can add an interaction variable, which is basically a new variable, which is male times experience. Why do we need this? Why do we need this interaction variable? We need this interaction variable to differentiate the impact that experience has for male, right? It could be that 1 year additional experience for male might not be the same as the 1 year additional experience for female. So just experience alone will not answer the question. So you are trying to add a new variable. Now this variable is a complex variable. It's a multiplication of male dummy variable times the experience. So let's say you have an entry which says, hey, there's this man called Kunal, and then he gets paid, let's say, $10,000. And then there's this female called Mimmansa, and then let's say she gets paid $20,000. So what happens here in this situation is you create a new variable called male times experience. And so for every male, you give it a 1. So you do 1 times 10,000. And for every female, you do 0. So 0 times 20,000. So this becomes 10,000, and this becomes 0. So basically, you're removing every entry with the female and experience, and you're just trying to look at male experience, right? So you add that variable, and then you run a regression. So what do we get? How do we interpret this is the most important. So the coefficient here, the constant of 40,000 says that when all of these is equal to 0, controlling for all other variables, this is what you get, right? This is how you read this regression output. It says when male equals 0, meaning female, when experience equals 0, and male times experience is 0, you get 40,000. This means a female gets $40,000. And that's how you read this. And then if you say for every additional male 1 year of experience, you get $500. And then for experience overall, independent of male or female, you get $1,000. And then if it's a male, then you add up 20,000. So the equation becomes 40,000, which which a female gets, right? That's the baseline. So understanding how to read the baseline, female with 0 years of experience, that's $40,000. And so similarly, male gets much more, right? So male gets 20,000 times male plus 1,000 times years of experience plus 500 times, if it's a male, times experience. So that's the equation. That's a linear regression equation. If you want to find out for a given male with 10 years of experience, what's the salary? So you add this, and then you multiply this by 10 and multiply this by 10, and that's the result you get. So basically, categorical variables help us with adding many more variables, because now you can add education as a third field. Then you can say, hey, I want to just look at male education experience, and so much you can add with an MRM. Otherwise, you will end up looking at each of these plots differently, which just becomes not manageable. So an MRM with categorical variables is important. Understanding how to use a dummy variable, understanding how to use the interaction is very important. And the key thing to keep in mind is the principle of marginality. So it's basically saying when you add this interaction, you want to add it only when both of its subcomponents are there. So male times experience is an interaction. In that case, what it's saying is male should be there as an explanatory variable, and experience should be there. You can't just add male and experience and either remove any of these components, right? So that's principle of marginality for how you can not remove those components when those interaction variables are there. So reading and understanding the baseline is the most important, and then understanding, like for this intercept, right? Like for this one, the difference for this 500 in a sense is basically the premium that males get for every years of experience, right? So this is the difference. If you were to run this regression for male versus female, you will see that male gets $500 more in the experience section. So that is the interaction difference. So how to understand and interpret the slope, how to understand and interpret the difference of the interaction variable is an important factor as part of categorical variables. All right, so that was the final section. So far in the class, we've learned just so much. So let's wrap up with a full summary. So the first is know it all versus learn it all, right? The growth mindset, being more of a geek than gut feel oriented will help you, because with relying on data, power comes on your side. It has much more insights. So use your intuitions for coming up with variables, explanatory variables, but not with what factor, how much weight I should give to this variables. Use data for it. So don't be an expert, be a geek. Big learning. Use the power of data on your side. One population has many samples. He looked at how random sample is so critical and the basis of all of the things that we've done so far. And you can take many samples, and there could be, from a given population, you can survey using 10 people, 20 people, 30 people. How am I going to use this? Well, if you get a survey in your company and everyone gets pinged to say, hey, everyone has to participate. I see that happening all the time. That is just not good, right? Because we've now learned one population has many samples, and those samples can be representative samples. So how the survey is designed, don't inundate everyone by taking those surveys. Don't participate in taking all of the surveys, because those surveys could be designed well so that only fewer people need to participate. If you ask everyone in the population to participate, it's just waste of resources and not needed. Sample mean has a sampling distribution. Central limit theorem, very, very powerful, right? So we learned about the normal distribution curve, how the sample mean, over time, when you increase the number of sample and means that you have, if you plot it, it will show a normal distribution because of the central limit theorem. Very, very powerful. is the basis for a lot of this work. We then learned about building confidence interval, right? So you can say, hey, this population parameter is, I'm 95% confident that it lies between this range, right? So we learned about building that confidence interval. And then the most important, p-value. A low p-value is evidence against the null hypothesis. Null hypothesis is essentially status quo. You're saying, hey, what we're doing is right, everything else is wrong. That's the null hypothesis. Stay where you are. And the alternate hypothesis, if you get a low p-value, that means it's an evidence against the null. You should reject the null hypothesis and move to the new future. So very important on how and when to reject the status quo null hypothesis. Type 1, type 2 errors, such a critical thing. Type 1, you're just too aggressive. Making mistakes, you're taking action when no action is needed. Type 2, you're lazy. You should have been taking action. There's things wrong and you're not taking action. So are you too aggressive? Type 1. Lazy, type 2. Very important to know, because when you're making those decisions, you want to make sure that you're not in the type 1 segment. And type 2 is also expensive. So you have to have a balance. Figuring out what is the right balance for you in an organization and its cost. Some type 1s can be expensive. Some type 2s can be expensive. How do you balance? How do you make the decision to have the right balance is super critical. Random experiments. Whenever you want to find out causality, remember, correlation is something that we've learned so much in this class, but correlation is not equal to causation. When you want to get to causation, run an experiment, run a random experiment, and that is the way to get to causality. It will remove all kinds of lurking variables, which are like factors that you're not thinking about, but they are there, and it's important to get validated through a random experiment. Regression line is nothing but minimizes the sum of squared of residuals. It's basically saying it's a line that is a prediction line. It's the line of the future. So in your interval, do not extrapolate. That's the key learning. Do not extrapolate. Use the regression line to predict for any given explanatory variable input what is the response variable output. Regression, Excel, powerful, very good. I've run so many regression analysis so far. What I found out is I ran the regression analysis to find out the alpha and beta for my stock portfolio. And I found out that I have very little alpha actually. And even my significance levels are very small. So real life is much more complicated than examples that we've learned so far. But I could now understand how to read the entire regression output. F statistics, R square, important, but then we realize that R square is not really, it doesn't have to be that high when you're trying to predict something that's very complex, right? Like for example, salary, right? R square here is 2%, right? Or 3%. It's very small, but there you could still have statistically significant. Like look at this t-stat. T-stat here is the prediction over standard error. It's above 2 is high, meaning this is more than 95% confidence, right? So p-value is less than 0.05. So look at this, right? So we learn how to weigh in R square. Adjusted R square is terms of figuring out which variables are really important, adding their weight. We learned about converting the linear fit, if it's not good, into a log fit. We learned about elasticity, percentage change in explanatory variable versus percentage change in the response variable. Huge learning. And then finally, when we do this regression analysis, there are 3 error conditions, right? 3 error conditions. What are those? Errors have to be independent. You don't want to see them clustered up or down the regression line. Then that's when you do the regression, always look at the residual plots. Always look at the line fit plots, because looking is so critical. That's the biggest another takeaway. Look at your data and check whether the errors are independent, meaning they are, there's a cloud above and below the regression line. It's not like concentrated above and below. Then second error condition, they have to be normally distributed. If you see the errors are not normally distributed, then that's the second error fault. And the third is heteroscedasticity, right? So which is the errors have to have equal variance. You should have the same variance. You shouldn't either be tapering up or tapering down. So very important to check for that. There's many more error conditions, spatial and temporal dependencies. But that's important for us to know. It's just a starting point. But these 3 are the most important to check for the residual errors. Confidence intervals. We we talked about that the parameter lies in the range. We are 95% confident prediction interval, 85% chance that you'll make $100,000 sales when you make a new petrol pump, or when you open up a new Starbucks, in our example that we looked at so far. So prediction interval versus confidence interval. Multiple regression is important when we have many more variables. And how do we interpret the slope for multiple regression? It's a partial slope, whereas in a simple regression, it's a marginal slope. So we learned about the directions, how to add weights to it, and then we applied it in the last section on finance, on our capital portfolio. Like, what is alpha? What is beta? Alpha, remember, is your edge. Alpha needs to be high. Higher the alpha, you have an edge. When stock market makes 0 returns, you still make a positive return. You want lower beta. Beta is nothing but volatility. It's the variance. If a stock market has 1% increase, and if your beta is 1.2, that means you can go up or down by 1.2, which is much more than the stock market. So you need low beta, high alpha, right? So very good. And then when we do that, we need to understand the collinearity between variables. If there is collinearity, then we can detect that by looking at the regression output. If standard error goes up, if the coefficients go up, R squared goes down, those are all like measures. And then if you check the correlation between those metrics, if it's high, then you want to check if those variables that are collinear are actually adding statistically significant weights. If not, you want to slowly, one by one, remove them. That's the big thing. And then finally, we learned about categorical variables, how to read the baseline, how to make sure that when we add an interaction variable that we don't remove the components, that we add them because of principle of marginality. And then finally, the key four themes, going not just using your gut, but also using data. So instead of just being an expert, also be a geek. It's important. When we do this, we can challenge the status quo effectively. With the help of data, we can challenge the decisions that have been made in the right way. So learning statistics is important. Learning machine learning is important because a lot of these problems are being made, are being reframed as a prediction problem. A lot of prediction in terms of like jobs matching is a prediction, like which job seeker should be matched to which job. That's a prediction problem, and it happens at scale. So many such problems are being framed as a prediction problem. Resume screening, automatic answer screening, so many such problems that machine learning and statistics is being used for. So it's very important for us to become more geeky, to become and understand these concepts, because otherwise we will not be able to demand excellence. Demanding excellence is pretty critical, and it's the basis for us to get to better decision making. Correlation is not causation, right? And remember, a lot of when we run an experiment, that's the best way to get to causation. And when you run experiments, remember that they are valid for that time period, and then things change, so you want to keep running experiments over and over. And we learned about how to run experiments. Y hat is more important than beta, which is basically prediction is more important than the relationship between the variables. So getting better at prediction, understanding how these prediction problems are framed is super important. And finally, the last bit, using data when we run these analysis, when we come up with these analysis, let us be very objective. Let us make the outcome of this statistical analysis simple, transparent, and objective. As my professor says, he put it in a really good way, but statistics is very powerful. Let us make it simple, objective, and transparent. And whenever you have assumptions that you're baking in, if you think your data is biased, be upfront. But when you're looking at data and you're looking at results, ask hard questions. If you don't get good answers, like, hey, what was the non-response rate? What was your how did you do sampling, right? Many such questions are important. Where do you get the data from, right? Very important. If we do all of that, then we are actually using the power of data behind all of us, and we are demanding excellence, getting better. So it's data, statistics, this opens up a whole new world. So far, we've only learned jargons and keywords, but at least we are able to now piece them all together, so that when we can take those deeper machine learning courses, or when we can go deep with